We're going to see how to manipulate a red-black tree in this video, so how to insert or remove into a red-black tree. But importantly, we have to be careful that when we change our red-black tree, we still have to maintain these 4 color properties, because these are what guarantee that the height of any red-black tree is big O of log n. So let's see how we would insert into a red-black tree, knowing that we have to maintain that the root is black, that all leaves are black, that any red node has black children, and that all leaves have the same black depth. Okay. So we can insert in the same way that we would insert into a binary search tree, because a red-black tree is a type of binary search tree. So let's say we wanted to insert 4, for example, and we were given this red-black tree to start with on the left. We would start at the top, find that 4 is less than 6, okay, so we go to the left. 4 is greater than 3, so we go to the right, until we find an external node, a leaf, where we can create a new node. Now the idea behind insertion now is we're going to, anytime we add a new node, we insert a new node, we're going to find where it belongs in our tree using that find algorithm. Start at the root and follow a root to leaf path, going to the left if it's less than, going to the right if it's greater than, until we reach a leaf. And then we're going to create our new node here. So when we create a new node here, and we fill in whatever our value is, we're always going to color that new node red. The only exception to this is if we have an empty binary tree, we want to keep that the root is black, so only in that case would we make our new node black. In every other case, we're going to create, when we create a new node, we're going to color that new node red, just like we did here. So anytime we insert a new node, we find where it belongs in our tree using the find algorithm for a binary search tree, and we color that new node red. By doing so, we maintain that the root is still black, so we maintain the root property. We haven't changed any leaves, so all leaves are still black. And we haven't changed our black depth, because we haven't added a new black node. So this leaf still has the same black depth as what it had before, because we only added a new red node in between. So for example, in this tree, we inserted our new red node here 4, and we have, as a result, still a valid red-black binary search tree. Now it is possible that we can violate the internal color property, which said that if we have a red node, all of its children must be black. So it's possible we have violated this. In this case, we didn't. This is a good, kind of an easy case of insertion that where we want to insert a new node, that its parent is black. So in that case, we haven't violated the internal property, we're okay. But it does become problematic when we try to insert if where we want to insert that parent node is also red. So again, we're maintaining the root, external, and black depth properties that we have. The only thing that we might violate is the internal property, which says that any children of a red node must be black. And this can happen if where we go to insert a node, its parent is red. So for example, if we have now this slightly different tree than what we had before, same values but different color properties. If we try to insert a new node 4 here, so we know this will be to the left of 6 because 4 is less than 6, the right of 3 because it's larger than 3, and we'll insert 4 here, and since we always create a new node and color it red, then we'll have our red node here, but we created what's called a double red. So this is a violation of the internal property that any children of a red node must be black, whereas in this case we just created a child of a red node which is also red. So in order to fix this, we have to kind of fix our tree a little bit, kind of shift around some nodes or recolor them perhaps. So when we insert a new node, we always color it red. But by doing so, we might violate one of the properties that red-black trees have, which is that children of a red node must be black. So when we do this, this is called a double red. So there's a couple ways that we could fix a double red, and which one we want to do is based on which of these cases we're in. So here I have an example where we created a double red here. Now this is the first double red that we created because we were assuming that when we inserted, we were inserting into an already valid red-black tree. So just by inserting here, if we ran into that issue where the parent is also a red node, then this is kind of the only double red which exists in our tree, which means that the parent of this node will also be black. Right? So there's a couple cases based on the kind of uncle of this new node that we added, or aunt of this new node that we added. So we're going to look at, here is our double red, and then we know that the parent of it will be black. The only question is, what is the sibling here? So Z was that new node that we added, V is the parent of Z, and W is the sibling of V. So W is like the uncle or the aunt of Z. So based on what color this other node W is, will determine which approach we should take in order to fix this double red. So if this sibling is black, we're going to do what's called a restructuring. If this sibling is red, we're going to do what's called a recoloring. So let's see how we would handle this first case. So we inserted a new node, we created a double red, and we have that the sibling of the parent of this double red is black. So in that case, we do a restructuring. So we want to maintain that internal node property that says that any children of a red node are black. So in order to do that, with the restructuring, we're going to kind of shift that, because we have two red nodes here, we're going to try and shift it so that we kind of distribute those red nodes, one on the left side and one on the right side. But we still have to maintain that we have the binary search tree still, and the other color properties that we have. So with the restructuring, again, this is the case that W is black. We're going to take the two nodes that are in our double red and then the parent of that also. So these three nodes together. So anytime we're in this case, we're going to consider these three nodes. And this is just showing one example, but we could have, maybe our double red is on the other side. So I'm going to show in, kind of fill these with red because I only have a red pen to work with in PowerPoint. So maybe we have our double red there, and here's our black node and black node here. So we have a few different cases of where that double red could be. Maybe this is a left child or a right child, or the parent is a left child or right child. So I'm just showing one kind of example here. But no matter which of those scenarios we're in, we're going to take these three nodes and evaluate where they would come in an in-order traversal and relabel them as A, B, and C based on that in-order traversal. So remember, since this is a binary search tree, any in-order traversal is taking those elements in ascending order. So we have here the nodes that store values 4, 7, and 6. So I'm going to relabel this as A, B, and C based on which one is the smallest, the middle one, and the largest one. So A will be the smallest one, B will be the middle one, and C will be the largest one. So this is the same order they would come in an in-order traversal. And then now that we've relabeled them this way, A, B, and C, smallest, middle, largest, we're going to shift them so that we have whichever one was B will be our new root of this subtree. A will be the left child and C will be the right child. Okay, and we're going to color the root to be black, and A and C will be colored red, however we had labeled those nodes as A, B, and C. Remember, this is just labeling them as they would come in an in-order traversal, which is just labeling them in ascending order. So A is the smallest, C is the largest, and B is the middle one. Okay, so now we kind of restructure them. Now we have B as the new root, A is the left child, C is the right child. And then we also have to carry that we have here kind of one, let's call it our first subtree. Here's our second subtree. And why is this the second one? This is just from left to right what we have. This is our third subtree. So there could be kind of a much larger tree here that I'm not showing. This is just kind of a local portion of our tree. So this is our fourth subtree. In our restructuring, we're going to essentially carry those trees with us. So we have here, this is our first subtree. We'll place this as our second subtree, our third, and our fourth subtree. So for example, whatever, just for our example here, based on how u, v, and z lay, the left child of u will now be the left child of a. The left child of z will now be the right child of a, and the right child of z will be the left child of c, and the right child of v will be the right child of c. Okay, so this is encompassing kind of a few different scenarios based on how our double red lies in our tree, if it's a left child or right child or so forth. So let me show you kind of what other cases this is including. Again, these are those cases where we created a double red in our tree, but we're in the case that the sibling of that double red is black here. Right? So it could be that this double red is a right child or left child, and that the new node we added is a left child or right child. So in any one of these situations we're going to consider the double red that we created and the parent of that double red, these three nodes, and we're going to relabel them based on how they would come in an in-order traversal, based on their from smallest to largest. So we're going to relabel them as A is the smallest, B is the middle one, C is the largest one. So we did this one in the last example. For the second one here, we would label this is our smallest, so that's A, B is our middle, and C is our largest. In this one, we would label here A is our smallest, B is our middle, and C is our largest. Here A is our smallest, B is our middle, and C is our largest. Just of those three nodes that we're working with, the double red and the parent of that double red. And however we had labeled them, we're going to set that B is the root, now kind of restructuring our tree. B is the root, we color it red. A is the left child of B, B is the root, we color it black. A is the left child of B, we color it red, and C is the right child of B, we color it red. Right? And then we carry those subtrees. So for example, in this one we have this is our first subtree. I'm just going to label them 1, 2, and 3, second, third, and fourth. Here, this is our first subtree, second, third, and fourth. And in this one, our first, second, third, and fourth. And lastly here, we have our first, second, third, and fourth subtree. Now when we restructure this, we carry those subtrees so that now this is our first, second, third, and fourth subtree. Right? So that way, in this instance, let's say if we're looking at this one here, whatever the left child of V was will be now the left child of this node A. And the left child of Z will be the right child of A. So you'll see here, this would still give us that, we're still satisfying the binary search tree property in the sense that, just kind of for this example, we have everything on the let's say the left of 4. This is everything which is greater than 2 still, but less than 4. So this is less than 4, but greater than 2. So same thing here. So we're still preserving this as a binary search tree. And we maintain that the root is black, leaves are black, leaves have the same black depth, but we just fixed that double red, so we now satisfy the internal property. Note that if we have to do a restructuring, if we're in this situation where we can do a restructuring, which again, this is that instance where here's that double red that we created, and we do a restructuring only when this node, this W, this uncle of the node that we added, when this node is black. So if we do a restructuring, this is kind of like we do one and then we're done. We don't have to keep going on. We've fixed all of the color properties that we have to. But we can only do this if this node is black. You can kind of try on your own if you're interested, try and do a restructuring also if this uncle is red, and you'll see that because of how our restructuring works, it kind of shifts so that those reds that we kind of joined on one side, it separates them so that we have one red on one side and one red on the other side. If we tried to do that again in this case, where we already have a red on the other side, we would effectively just move that our double red is now on the other side, on the other subtree. So we need a different way to handle this case. And in this one, when the uncle of our double red is itself also red, we're going to do what's called a recoloring. So let's see what that recoloring is. So again, we have that the uncle of our double red is itself also red. And if we encounter this situation, we're going to change just kind of these three nodes here. So we're going to keep that the node that we added, it's going to stay red, but we're going to shift, kind of drag down this black to both of these nodes. And in doing so, that way we're not going to change the black depth, but we're going to recolor them so that now these two nodes, just these two nodes, are going to be black, and this node is going to be red now. So it's kind of like shifting that black down so that we haven't changed the black depth for anything in this left subtree or the right subtree. The black node, which is contributing to our black depth, is just now this node and this node separately. So with a recoloring, we created a double red here, but we're going to color these two nodes black, and we're going to color this node to be red. So this will locally fix our double red, but it's possible that by doing so we maybe propagated this double red up our tree, because it could be that maybe the parent of this node is also red. That would have been fine in our old tree before we had changed it at all, but we had just colored this node red as well, so it's possible we propagated this double red up our tree. Okay, so just kind of quick recap. With a recoloring, we do this only when this node is red, and when that's the case, we color these two nodes to be black and this node to be red. I should note that if this node here is the root of our tree, in order to maintain that our root is always black, we're only going to color this red if it's not the root. So if we're in that sort of odd edge case where we've gone all the way up our tree and this top node is the root of our entire tree, then we don't color it red, but otherwise we do. Okay, so now that we've colored these nodes black and this node red, if we created another double red, kind of moved it up our tree, we fixed this double red here, but it's possible we propagated that double red up our tree. Then we have to reevaluate again which one of those cases we're in. Should we do a restructuring or a recoloring? So let's see how that would look algorithmically. So we go to insert an item. This is the element and the key associated with that item. We use the same find algorithm that we would for inserting into a binary search tree to figure out what the insertion node should be. So we start at the root, we go to the left or to the right based on how this key compares with that node. So that this step alone takes log n time because we follow a root to leaf path, which is the longest possible path is the height of our tree, and we know for red-black trees that the height is logarithmic. So we find where this new node belongs. Then once we find it, we create a new item and we color that new node that we just created to be red, assuming that it's not the root. So we color that new node red. That takes constant time. So we're creating a new node and setting a color attribute. And then in our step 3, we're going to check to see, did we create a double red? If we didn't create a double red, if we added a new node and its parent was black, we're okay, we don't have to do anything else, we're done. But possibly we created a double red if the new node that we inserted had a parent which was already red. Then we created a double red. What should we do next? This is based on those two cases. Should we do a restructuring or should we do a recoloring? So here's the double red we created. Let's say here is the parent of it. And again, I'm going to keep those just outline vertices black. If this sibling is black, we're going to do a restructuring. But if the sibling is red, we're going to do a recoloring. So based on the sibling of, here's the new node we created, here's the parent of it. I think in the previous slides we had this labeled V, and here's that other node, the sibling of V, called W, we're checking to see, is this black or not? So if this is black, we're going to do a restructuring. When we do a restructuring, we just do one, we fix all of those color properties that we have. We don't have to keep going anymore. We didn't propagate anything up. But if the sibling of this node is red, then in that case we have to do a recoloring, and it's possible when we do a recoloring that we propagate that double red up our tree, in which case we have to check again, did we create another double red somewhere further up our tree? So maybe we fixed this double red, but in doing so, we would color these nodes to be black and this node to be red. Maybe the parent of that node was also red. So we fixed this double red, but we kind of moved it up by 2. So in that case, we're going to check again, based on this new node, did we create another double red? Right? So this is just returning the parent of V. Right? So this will return this node here. To check, did we create another double red? If we didn't, then we're okay, we're done, we don't have to keep going. But if we did, then we have to check again, okay, if we have this double red, evaluate which of those 2 situations we're in based on, here's the double red that we created now. It's a little bit further up our tree. Now we have its parent, and it's this sibling or uncle of this node that we had created our double red from. So again, based on the color of this uncle, we're going to determine if this is black, we can do a restructuring. Just one, we're done, we don't have to continue anymore. Or if this is red, we have to do a recoloring and then check again, did we propagate that double red up our tree? So notice that when we do a recoloring, just one recoloring is constant time because we're just changing a constant number of color attributes for those 3 nodes. Same as restructuring. One restructuring just by itself is constant time. One recoloring just by itself is constant time. But the issue is we may have to go through these loops, big O of H times, and this would happen if we're unfortunate that every time we do this we're in the situation that we have to do a recoloring, and we're unlucky that we keep creating another double red, fixing our local double red, but kind of moving it up the tree. But fortunately, the height of our tree is bounded, which means we're not going to execute this more than log n times. So our total running time for step 3 is log n, which means for insertion, we can insert into a red-black tree in total big O log n time, in logarithmic time. Okay, so we're going to look at delete next, just kind of briefly. Now, our algorithm for removing an item from a red-black tree is very similar to how we would remove one from just a regular binary search tree. So we can always make sure that we're in that case where we have that the node that we're deleting has at least one leaf. Otherwise, we take the next one that comes in order traversal, we swap them, and then we're in that nicer case. So we're going to use the same delete algorithm we did for binary search trees. And let's say we're deleting node V. So V is the one that we're getting rid of. If we have that the node we're removing is red, or it has a red child, then we can do this without creating any problems. We still satisfy those 4 color properties. So in this case, we would kind of contract. We would delete that node that we want to delete and its leaf, and then color the resulting node here black. Okay. So that's what we have in each one of those instances. We're deleting this. We're taking now, once we get rid of this, following our binary search tree deletion, then the new right subtree of 6 will be the left subtree of 8 now, since this was that leaf. And in doing so, we remove this and we color that node that we had placed here to be black. So when we do this, we maintain that we haven't changed the root at all, it stays black. We haven't changed any leaves, they stay black. We didn't add any red nodes, so any children of a red node are still black. But it's possible that we violate the depth property. So we have to be careful to fix that in our tree if we created that issue. So an example of when this would occur is, let's say we're given this subtree, and the node that we want to remove is black and its children are black. So that means that by removing this node, when we get rid of it, we're going to change the black depth of this node. So we're going to kind of get rid of these things, and then when we move this node up, we decrease its black depth because we got rid of one of the black nodes that was contributing to its black depth. So in order to fix this, so we're going to call this basically a double black. So we had a double red when we insert, we can have a double black when we remove, and the reason why we're calling it a double black is because we need some way to basically say that this node has two black nodes that are contributing to its black depth. So in order to fix this double black, we have many cases to consider, much like we did with a double red. But rather than going through each one of these cases, because we have more cases to consider here than we did with a double red, these cases aren't complicated. They're actually very similar to what we did when we encountered a double red, but they're tedious. And it would take probably another lecture to go through each one of these scenarios of exactly how to fix a double black upon removal of a node in a red-black tree. And I think that our time is better spent learning some other topics. It's important just to know that when we remove from a red-black tree, it's possible that we can create what's called a double black, in which case we do a restructuring, and one restructuring and then we're done. Or we have to do a recoloring. By doing a recoloring, similarly, we may propagate up our tree a double black. Or another situation, which is called an adjustment. So it's kind of a combination of those two things. But we can do all of this in log n time. So you should be able to find and insert into a red-black tree and understand which one of these cases you're in during an insert, that depending on the color of, if here's that double red that we created during an insert, if we created a double red, here's the black parent and the sibling. If the sibling of our double red is black, then we do a restructuring. If the sibling is red, then we do a recoloring. If we do a restructuring, we fix our double red locally and globally, so we can do one restructuring and we're done. If we do a recoloring, then maybe we definitely fixed it locally, but maybe we just kind of moved that double red up our tree, in which case we have to reevaluate again. Did we create a double red? If so, figure out which of these two scenarios we're in to fix it. So insertion we can do in log n time. And for deletion, it's important for you to know that deletion also takes log n time. And this is based on the height of our tree again, and that it boils down to an easy removal if the node to remove or its child is red, or that we're in one of a few cases. Either we perform a restructuring, one restructuring and we're done, or we do a recoloring, in which case we might have propagated up double black up our tree, or we do another minor tree modification called an adjustment. So if you have any questions, let me know, post on Piazza, reach out. I encourage you to try an example of inserting into a red-black tree, which is in the link below this video as well.